All right, so let's begin. Welcome everyone to this afternoon session. So I'd like to start with a public announcement, which is the talk of Elisabetta Rocca, which was originally scheduled for tomorrow, Wednesday at 2, is instead moved to Thursday at 2. So there will be no talks tomorrow afternoon, just the morning session, and then you can enjoy working together or seeing beautiful Toronto. And then on Thursday, we have an afternoon session starting at 2. And no posters, okay? Unless we get many requests for posters, then we can have parallel sessions, okay? But we got too few requests. So for now, no talks tomorrow afternoon, session at 2 on Thursday. All good? All right. Unless Eleanor wants to present by herself the poster. we can still have posters around. We'll discuss that. Sorry, I put you on the spot. All right, this said, so it's a pleasure to introduce a compatriot, Giusy Mazzone from Queens, and she's going to talk about partially dissipative systems, modeling fluid-solid interaction problems.
Thank you, Fabio, and thank you, the organizer, for the invitation, and all of you for being at my talk. So today I'm going to talk about some fluid-solid interaction problems, and these kind of problems have kept me busy still since my PhDs. I have studied quite a few problems. Some of the majority of them, let's say the 3 cartoons that you see here, are basically fluid-solid interaction in which the fluid is completely enclosed by a solid, which could be rigid, may or may not have also an inner core, but could also be elastic. Okay, I also put a cartoon on a slightly different problem, and today, though, I'm going just to talk about some of the work that I have done with my colleague Francesco Cellarosi from Queens and my student Anil Bandutta, again from Queens, who just defended a couple of weeks ago. And this problem is about a fluid-filled rigid body, which is heavy, so there will be gravity applied to it, and then a fluid-filled elastic solid, which is my work, and there is also a little bit of work with my other student, Jerin, who is hoping to defend next year. But what all these problems have in common is the following fact. I like to call them partially dissipative, in the following sense. If one tries to write down what is the motion governing, the equation governing the motion or the deformation of the system, one can, in a very abstract way, write down an evolution equation, an ODE, an ordinary differential equation on a Banach space in the unknown variable u, and this variable u has a particular structure. One can identify 2 components, v and omega, and v is dissipative, is a quantity, is a physical quantity that is related to the fluid, and omega, which my fluid will be usually Navier-Stokes fluid, so viscous incompressible fluid, and the component omega is a physical quantity related to the solid part. And then if one wants to study the PDEs, the first, let's say, step is to do zero-level energy, say L2 estimates, if you like, of your PDE, and you end up, sorry, too fast, you end up with an energy equality or inequality, but let's focus on the equality side because my application will be in this structure, which look like this. You have an energy, typically this will be a kind of mechanical energy of the system, which dissipates only in the fluid variable, of course, with the suitable topology. So I'm being very abstract here, very, very hand-waving here, just I will be very, very precise for the next 27 slides. The point is that for this kind of ODE, with this kind of energy, this kind of, let's say, energy inequality may not be enough to show existence of solutions. And this will be the first application that I will give you, or if it does provide enough, let's say, boundness, uniform bounds, so that you have compactness in a Galerkin method, say, so you can construct a solution, you may lack information about the long-time behavior and the stability property of the system. And this will be the second application of this talk. So let's get started. Of course, the point that I want to make in this talk is that at the moment, depending on the problem that we are dealing with, we have different techniques. But for the last problem, actually, we came up with the more abstract way to deal about stability problems, and then which will go back to this abstract ODE that I showed you in the previous slide. So let's get started with the first problem. So what do you have? You have an elastic solid, let's say a thick, is a 3D elastic solid, a thick golf ball, for example, and assume that it has a hole in the middle and is completely filled by a viscous incompressible fluid. Now, assume that there are no external forces, so you may have a reference configuration in which this solid is stressed. Then you have your stopwatch. You start by looking at deformation. Once you give another, let's say, deformation and perhaps a velocity to the solid and to the fluid. And you let it go, and you want to try to understand the dynamics of this system. If you want to write the equation governing both, and it's important to note that both the motion of the elastic solid and the fluid are unknown, one has to choose the variables, okay? Let's say standard variable for the elastic solid is displacement. And typically from a continuum mechanics point of view, you look at the deformation using the Lagrangian description, which basically you take your favorite point and you follow along the trajectory and calculate the displacement along the trajectory. Whereas for the fluid domain, typical variables, and the variables that I will use will be the velocity and the fluid pressure, but in their Eulerian description. And what you do, you basically look at the volume and the fluid volume at time t, and you calculate your velocity and pressure there. This is typical for from the very general fluid mechanics / continuum mechanics point of view. Of course, you can go from one description, the Lagrangian, to the Eulerian description, once you know what is the flow map, which is the map which basically, given the capital X position of your favorite point, either in the fluid or in the solid, maps it to the position at the same point, or this is exactly the same physical point, but that occupies the position small x at the t time. And of course, since I'm not prescribing any motion here, chi is another unknown of this problem. We have to make some assumptions on chi. So one assumption, in principle, chi is defined both for the fluid and the solid. I will be mainly interested for chi in the solid, as you will see in the next slide. But in general, what are the assumptions that I make? That the solid undergoes infinitesimal deformation. Basically, the gradient of u of the displacement are small. And for the fluid is incompressible, which means the Jacobian of the gradient of chi, which are called deformation gradient, will be equal to 1 at all times. And with these assumptions, the equations of motion read as follows. So we have the first equation is the so-called Navier equation of linearized elasticity. You have never seen this already, this equation, during the distinguished lectures of Professor Kanich last week. So if you want to look at it, P is what is called the first Piola Kirchhoff stress. If you want to expand this divergence, it's a second order perturbation of the Laplacian. So you can think about the first equation as a second order in space perturbation of the wave equation. The blue equations are the Navier-Stokes equations for the fluid, viscous incompressible fluid. The T here is the Cauchy stress tensor. And then you see that the fluid, so omega B, when there is no T, everything is in the reference domain. And again, the reference may or may not be the initial condition. But now here you see a T because I'm looking at the Navier-Stokes equation in the moving boundary omega T LT, which is the image through the map chi that I showed in the previous slide, which satisfies this flow map. Chi is the flow map associated with the fluid velocity. And now we have boundary conditions. So gamma B is the outer domain of the solid. So I'm imposing a stress-free condition. From a mathematical point of view, this is a kind of Neumann type-like condition. And we are basically saying that there are no forces applied on the exterior. In particular, though the solid can rotate and translate, but there are no forces, external forces applied on the surface, on the outer surface of the solid. And these conditions, here, which look very complicated, are nothing else continuity of velocities and continuity of stresses, continuity of forces at the fluid-solid interface. So objective of my work, or this first part of the talk, is to show you, present to you a local well-posedness result for some initial data in some class that I will show you in a second. Of course, these are strong solutions, so they will satisfy the equation of motion almost everywhere in space-time, and as such, the initial condition requires some compatibility conditions, but I will not talk about that now. However, our smooth solutions satisfy this energy balance. You see here in the square parentheses, this is the mechanical energy of the system. And you see here the dissipation, which I want to draw your attention, comes only in D, and D is the rate of deformation tensor, is just the symmetric part of the gradient of V. And this is not enough because we don't have Poincaré for the simple reason that the velocity is not zero in principle on the fluid-solid interface, and the solid is undamped. So this one, together with the fact that this expression does not give enough information on chi, make basically this equation, as physical interesting as it looks, at the moment useless, okay? Or useless for the construction of the solution. Of course, fluid structure interaction, we had 3 lectures last week about it, have been widely studied. Let's say the novelty of my approach is basically I'm considering 3D interactions in which now the fluid is within the solid. Whereas a lot of work has been done for the dual problem of the solid in the fluid. So, but as customary as in the previous references, at least when dealing with the strong solution, is rewriting our equation in a fixed domain. And you do this by using your change of variable chi and mapping your equation back in the reference configurations. And of course, you pay the equation for U does not change because that was already Lagrangian. But you pay some prices, you destroy the structure of the Navier-Stokes equation. In particular, yes, you get rid of the nonlinear term because now you are Lagrangian, but then you see that your viscosity or your stress term or the viscosity term becomes highly nonlinear. F, remember F is the gradient of chi, and chi is basically, V is the velocity of the derivative of chi. So we try to study solution to this, and we can prove that for sufficiently, I would say, low regularity within the realm, of the previous references, we can show that there exists any size, there exist local in time solutions. And in particular, you can find a volume preserved diffeomorphism. So you can go again back and forth between Eulerian and Lagrangian formulation. So these are any data, small time solution. I didn't write the regularity class. You can think about the fact that they preserve, let's say, the velocities, roughly speaking. Okay, not very precise, but this is what is happening. So let me give you an idea of the proof. So the proof goes in the following way. There will be a first fixed point argument. So I give you a chi. So I give you a deformation mapping. And then I solve the previous equation where now the F, or if you like the cofactor matrix, but of F is given, because once you give chi, then you can find your gradient, and then you can plug it in the red parts. So now you are solving for U and V, and now the equation becomes linear. And assume that you can find U and V. Well, once you find V, then you can solve for chi and hope that you get a fixed point. Okay, so this is the plan. So then let's focus on the problem in which now chi is, so these F here are given, and let's try to solve for U and V. And now I put these colors here just because I want to draw your attention that the PDEs are the first three equations, and they are decoupled from each other. They don't see each other. The only way that they see each other, this is in general also the previous case, but in particular in this case, is through the fluid interface. So we will take advantage of this by splitting the problem into a fluid problem and a solid problem. So this will require another fixed point argument. And this is what we do. So now fix the velocity and the pressure. Okay, they don't have anything to do with the chi. So you have your chi, and now is fix your velocity and pressure, and solve for this equation for U with this boundary data, this Dirichlet type boundary data, and this Neumann type boundary data. And now if you find U, and you are lucky enough that you can define what is Pu dot n on the boundary, you have enough regularity for that. You have to be very careful with the regularity. Remember, Pu dot n is a kind of Neumann condition, kind of normal gradient. It's more complicated than that, but it has that kind of regularity you need. Then you can feed the fluid equation and solve for this equation, which now is like Stokes' problem, what these some forces. What did I do? Well, I went in the fluid equation, I put all the terms which they don't match. So this will be the given tildes, 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 and I add and subtract the terms to make the Stokes equation appear, the divergence of this one appearing. Okay, so now I have to make sure though that this whole procedure works. And so for the elastic problem, we use some results which were very well known for the wave equation with the Dirichlet boundary condition, and we basically rediscovered with my student for this equation, which, as I said, is a second order perturbation of the wave equation, but it also have, let's say, mixed boundary condition in the sense you have two portions of the boundary with different boundary conditions, Dirichlet and Neumann type condition. And basically, we show that, in fact, the solution that we have from here corresponding to the given initial data has enough regularity. And this regularity of Pu dot n that we find on the boundary does not come from the energy, standard energy. You have to do other estimates. Okay, is what is usually in the wave equation. These are called hidden trace regularity. For the normal gradient, we are doing this, we are uncovering hidden trace regularity for this Pu dot n. And this is just enough now to go into the Stokes problem, non-homogeneous Stokes problem with the prescribed stress, We use this result by Grub and Solonikov, and all the estimates turn out to be well for the given forces. And then we can build now the fixed point for that maps V tilde P tilde to the VP coming from here. So basically, I think I wrote it, if T is sufficiently small, that the existence time is sufficiently small, basically we can solve this problem. But now we have our V satisfying this problem, and then we find the chi, and we close the fixed point that I showed you in the previous slide. Okay. So this is the first problem. It was a problem about basically existence of solution, and the fact that usually the standard energy equality or inequality that we may get may not be enough. It was a hand-on kind of methodology, because we have our equation, we struggle with the estimates, and this is what we do. This second problem, though, one may think that is simplified in a sense. I've studied this now for a long time, but we ended up with some very general results to study the stability of evolution's equations, which actually apply also to the physical problem. And this is the second part of my talk. So what is the system? So the system is, as before, is a fluid filled solid, but now we assume that the outer solid is a rigid body. And we assume that it's constrained to rotate around a fixed point, O, is a spinning top, if you like, toy, or a pendulum, a Foucault pendulum, for example. Of course, there's to have the drop of water inside. But now the motion happens under the force of gravity. And we want to see what happens now to the long time dynamics of this system. So these are the equations. Now, what is the advantage? I have to speak. What is the advantage of this formulation? Before I present it to you, let me tell you with the picture is that now, compared to the previous problem, chi, the deformation mapping, we know what it is. We know that it's a rigid body motion. So we know what it is. We don't know the angular velocity, the velocity with which is rotating this solid, but we know the structure. And more than that, we can find, I'm going too fast, too excited to present the result. We can find a frame of reference which is rotating with the solid, and basically corresponding to which the volume of the fluid becomes time independent. So what is this change of variable? I just said it's just a rigid body motion. And what are these particular three axes that I can find? Are the so-called principal axis of inertia of the whole system with respect to O. If it was a rigid body only, you can think about these three axes if you think about no symmetry whatsoever, about the three preferred axes that the body would move if it was for inertial motion, so no other forces. And it carries the information about how the mass is distributed within the system. And the same thing happens, is just the rigid body dynamics, but now it also has the fluid part. Okay, so now I'm writing one other thing that I have to say. I make a simplifying assumption. It's just simplifying because it makes the equation looking nice, does not change the analysis at all, that the center of the mass of the whole system is along one of these axes of inertia. And this E3 axis plays a role in because imagine that the gravity is applied exactly at G. So this is the special axis that we will have in our system. So now here are the equation. I called omega my bounded now domain, time independent. The first two equations now we can recognize as the Navier-Stokes equations. I have additional terms here, which is this term here and this term here, and one hidden in the pressure, which is just Coriolis centrifugal forces, because again, I'm writing the equation with respect to a rotating frame, and is rotating with angular velocity omega, which is, as I said, an unknown of the problem. The gravity here now, since I'm with this bottle here, so if I am on the body, imagine that this reference frame that I'm writing the equation with respect to which I'm writing the equation is rotating, which means that with respect to this frame, the gravity or the direction of the gravity is unknown. Of course, the magnitude will be always 1, or yes, in this case 1, but the direction is changing, and this is rotating with the same angular velocity as the solid. Okay, so this equation read here is the same as saying that in the inertial frame, so in a frame, let's say with the far away stars, the gravity is constant, but not in our moving frame. And then the third equation is the balance of the total angular momentum of the whole fluid solid system with respect to the fixed point O. So this is an ODE. Omega, as I said, is the angular velocity. And, you know, if for a moment you were forgetting about being in a fluid, this is exact, and put A equal to 0. A is just a linear function of V. Is the only thing that you need to know about A, that is just a linear function of V. This is just rigid body dynamics. Okay. And this I is the inertial tensor, and is diagonal because the three axes that I chose are exactly the eigenvectors of this vector. And lambda 1 and lambda 2, lambda 3 are the parameter that encodes how the mass is distributed within the system. For example, if I was just the identity, I'm just saying that you have a completely symmetric fluid solid system, whatever that means, because you have the fluid inside. But is basically saying that the mass and the mass of the body and the mass of the fluid with the density of the mass and the fluid and the volumes of the mass of the solid and the fluid are such that I is the identity. Okay. But in our case, lambda 1 and lambda 2, lambda 3 are different, and they play an important role. As you know, in rigid body dynamics, they play an important role also in our stability problem. So at the fluid-solid interface, we have just one boundary condition of the fluid in this case, because the outer solid is rigid. We have no slip boundary condition. V is in this case the relative velocity. Sorry, I should have mentioned before, is the relative velocity of the fluid relative to the solid. This is why now the velocity is 0. Okay, is the absolute velocity minus omega cross x, if you like. And now you write your energy balance. Now this you can read it right away. How you do it? You take the fluid equation, multiply by V and integrate over omega. And then you combine the terms that you get from the second equation. And you end up with this one, which is really in the parentheses, the mechanical energy. The first term in red here is kinetic energy. Of the fluid and solid. The first two terms, although there is a minus sign here, the first two terms, I said A is just a linear function of V. So this is actually does define a norm for V, which is equivalent to the L2 norm, despite what it looks, but is an equivalent norm for V. The rest is basically encodes the kinetic energy of the solid. Then you have the potential energy, and you have your dissipation. And now this, I would say that is a true dissipation, because this is the gradient, and you also have Poincare. But you also have a constraint, and the constraint of your motion is that so this term here, I omega minus A, is the total momentum of the fluid-solid system with respect to the fixed point, and then its component along the gravity has to be constant at all times. Okay? So with these two equations, one can prove existence of solutions and can also prove that at least in the L2 norm, V goes to 0. And now follow me. A weak solution, I mean, for the fluid are Leray-Hopf solutions corresponding to data in L2, which are weakly divergence-free, and the normal component is weakly 0. So these are my solutions. So one can believe that this solution exists. And basically what you have that because of the viscosity term, the velocity will also go to 0. Then what we would get if the velocity goes to 0, now follow, actually I'll try to write it here. For the moment, I'm not being very formal. If the velocity goes to 0, what we have in the Navier-Stokes equation is not true along weak solutions, but you just follow me. You have that omega dot cross x will be equal to minus grad p. And allow me also, okay, I can leave it or just drop this guy into the pressure, which basically is saying that the velocity gradient has to basically match the centrifugal forces. But now from here, if you take the curl of both sides, you will get that omega dot will be 0. So V, I'm assuming that is equal to 0 because of dissipation. A will be 0, it's just a linear function of V. And I'm being very formal. From Navier-Stokes, I get that omega dot will be constant. From the constraint, I will get that gamma dot will be constant. What I'm left with? I'm left with the steady states. And steady states basically are those for which the fluid is at rest with respect to the solid, and omega and gamma have to satisfy this system of nonlinear algebraic equations, which is omega cross I omega equal to beta squared E3 cross gamma, and omega V equals 0, and I have omega cross gamma equals 0. What are these steady states? These steady states, I wrote explicitly what they are. And I'm sorry, here there is a typo. I just noticed. The more you read the slides, the more you find the typos. The C should be lambda 3, and the A should be lambda 1. Okay. So what are these? Some of these, we can characterize all of them, but for the sake of this talk, depending on the mass distributions, so the choice of lambda 1 or lambda 3, lambda 2 and lambda 3, you have the following one, just those distribution. You have, this is your solid, so keep in mind that this will tell you how this is, the tip will tell you how it rotates. You either have permanent rotation, so the solid is rotating with constant angular velocity along the gravity, either upward or downward. Or you have SP1 and P2 that they are steady precession. What are these? The solid is rotating by describing a cone of constant angle along the gravity. So it's just rotating like this. Okay, and you have up and down, and then depending on how you choose your parameter, lambda 1, lambda 2, and lambda 3, you have either SP1 and SP2. You have more than this. We characterize all of them, but for the sake of the talk, also for what we can prove, we just choose this. So here I'm not considering the case, exactly the spinning top case, if you like, which will be lambda 1 equal lambda 2, lambda 3. Lambda 3, remember, is this spatial axis that passes through the center of mass.
So there's a mutation or something?
No, there we cannot, we do have some partial result, but the method that we developed does not apply yet to show that case. But we do have some results, but it's a different method. Yes, they are given. You give me a solid, and the kind of fluid, and you can calculate what are lambda 1, lambda 2, lambda 3. Yeah. They are eigenvalues of a tensor that you know what it is. Is their principal moment of inertia, yes. So what I have said basically goes almost all through, because one has to show why the argument on the board works. So corresponding to initial data in L2, one can find the global in time, any data global in time, a Liouville solution for the fluid. And one can show that, okay, you give me your initial data L2 in L2, you find your solution, and there exists a time, the solution will be just in the regularity class. This is the Liouville regularity class. So V will be L infinity, 0T or infinity if you like, L2 of omega, and then intersected with L2 0T H1 of omega. So just in this regularity class, they would satisfy the equation in the weak sense. However, there exists a time, T naught, which depends on your solution, such that after that time, the solution becomes smooth, satisfies the equation, has enough regularity to satisfy the equation almost everywhere in space-time. In particular, you can define a semi-flow, you can define a dynamical system, and and actually V goes to 0 in the Sobolev norm W12. Okay. So basically what we have is the following, that you start with your initial condition. So I call it now U naught. I go to the notation. So you give an initial velocity and initial angular velocity for the solid, and an initial angle, basically, or tilt angle. And then you can construct a weak solution, and this solution can be rough. We don't know if it is unique, we don't know if it's regular, otherwise we would be rich, because it's Navier-Stokes, and it's 3D Navier-Stokes. However, there exists a time in which, and this time depends on the viscosity, the bigger is the viscosity, the earlier it comes this time, in which the solution becomes smooth and somehow is approaching the set of equilibria that I showed you before, which in our case actually are manifold of equilibria. So now the question is, what is happening? Is this solution that I'm constructing going to fool around the set of equilibria for the rest of its life because it's global, or is going to hit a point, so converge to the point of the equilibria? And basically what is turning out is that, well, the time T naught, or let's say U T naught, you can choose it, could be sufficiently close to the, because it's going close to the set of equilibria. So everything boils down to study the stability of the solution for initial data close to the equilibria. And this has been done. I did it majorly with Galdi from University of Pittsburgh, using different methods, Lyapunov theory, or linearization. And I will go back to this method in a second. But in order to do that, I'll now go back to the third slide, in which I showed the evolution equation, because what I'm going to tell you, it is actually general facts that in general happen if you are working with an ODE on a Banach space, and you can choose Rn if you're comfortable with that. For us, will be functional spaces. And about the stability of solution to this kind of problems. And everything I'm saying now would be very abstract, but all the problem that I showed you can be recast in this form. But I just want to drive you through the methodology. And it's somehow simplified because it's general. So consider this ODE on the Banach space. What are the assumptions that we make? This is a semilinear equation in the parabolic type, in the sense that you can identify a linear operator, which is sectorial, is a generator of an analytic semigroup with stable spectrum. So solution when f is equal 0 here are exponentially stable. But our equations are nonlinear, and our nonlinearity is such that basically it's a C1 function between some, defined on some, let's say, interpolation space between the domain of A and X. And let's say for a sufficiently regular initial data, one can prove that the Duhamel formula or variation of parameter formula does lead to a solution, which may be just, if you take any initial data, could be just local in time, in principle. Again, here I'm just very abstract and general. We are looking at stability property of equilibria. What are the equilibria? Equilibria are solution to the basically steady state problem AU equal to FU. So now if we want to study the stability properties of equilibria, then we have two methods. One is the Lyapunov method, which is based on constructing a Lyapunov function. And sometimes, depending on the problem, already problems with rigid body dynamics without fluid, constructing the Lyapunov function, especially for instability, I would say, is not a trivial task. Or you could do linearization, or what I call nonlinear spectral stability. So what you do, you have your ODE, you subtract your equilibrium, and then you linearize the problem. So this L, which is what I call linearization, contains A minus the Frechet derivative of F at U. And then I throw all the quadratic term into G. And I focus on this problem, studying the stability of the zero solution. Spectral stability analysis, what you do, you drop the nonlinear terms. And you look at the spectrum. And depending on the spectrum, you say whether it is spectrally stable or unstable, depending on how, for example, if they are all eigenvalues and they are all positive, in this case, will be exponentially stable. And then what you hope for is that, well, whatever you get, whatever information you get from the spectrum, you can apply to the nonlinear problem. And for that one, you need a kind of linearization principle. And one that I teach, for example, in the class is basically saying for ODE now in Rn, well, if 0 is not in the spectrum of L, and you don't have imaginary eigenvalues, then you are good, okay? The problem is that in our application, this can be extended, of course, in the infinite dimensional settings, and in our applications, we do have 0 spectral value of L. So we have to go around it. Then I'm just here recalling the assumptions. Here I wrote what is this X alpha. We are PDE people here. You can think about Besov spaces or Besov potential spaces, interpolation spaces between, say, the ambient space LP and whatever is the domain of your operator. Now I need some more information about the spectrum, and I put these are purely geometrical assumption on the spectrum. I basically assume that the set of equilibria around, at least locally, forms a C1 manifold. And 0, which is a spectral value, is semi-simple. Here is the definition. If you want to look this at Rn, you're just asking that algebraic and geometric multiplicity is the same in Rn. But this is more complicated than that. And then you add that. So basically what you have a center manifold. But now, which is maybe tricky, you just make the assumption that does not contain periodic solution.
So what are the N and the R?
N is the null set of L, and R is the range.
Null set.
And the range. So under these assumptions, then we say that the equilibrium is normally stable if, and keep in mind that this is just, you know, what are the conditions on A and this geometric condition on the equilibria, is normally stable if now L, remember that L has two parts. It has A, which is stable, minus the Frechet derivative of your nonlinearity at the equilibrium. Okay, I think I have the definition. I'm going too fast. Okay, it's here. This is L. Okay, A is stable, but this linear operator, what can do and what it does in our application is to move the spectrum around, in principle, and this is actually what happens in our applications. So we will say that the equilibrium is normally stable, is now the whole L has a stable spectrum. And so what you expect it is the least spectrally is stable, exponentially stable, and it will be normally hyperbolic if L has an unstable part. And what you can say from here is that the equilibrium will be unstable.
Sorry, why is it enough to consider the real part of the spectrum?
I'm sorry?
Why is it enough to consider the real part?
Because the operator is sectorial. Under this assumption, so after this definition, we are ready to show the first result, to just present just the statement for you. This is not very surprising. I more or less had it. You know, Anirban was good enough to rephrase it with you know, less conditions. But if you have a normally stable equilibrium, then it's exponentially stable in the following sense. It's stable in the sense of Lyapunov, and if you take sufficiently with initial data which are sufficiently close to the equilibrium, you're actually converging exponentially fast to an equilibrium, which is not necessarily the one that you started from. And this is because you have this center manifold in the middle. So this is not that surprising. What was surprising was this theorem. Oh my, going too slow. Okay, which says that if your normally hyperbolic equilibrium is unstable, okay, is spectrally unstable, is understandable, but you have this property, which I find it quite surprising, is a lot of math following my argument. If you have your solution, say you start sufficiently close to your equilibrium, and you happen to know that your solution exists globally, I told you the variational parameter formula may be just local in time, but assume that it is the maximum existence time is infinity, and you happen to know that now the solution gets close to the equilibrium and stays close to the equilibrium at all time. Although you may reach an unstable manifold, you must converge to an equilibrium and exponential rate. So you are still attracting solution, roughly speaking.
So E there is a set of all equilibrium?
Yes, yes. So I'm not discussing the proof of this. Please come and talk to me afterwards. I think that this goes beyond the scope of this workshop, but this works in our case. It's exactly what is happening in our case. This is the topology that we have. And basically, what we were able to show that for a large set of initial data, which actually my student Anirban removed in his thesis, I just put one in the paper, but he could relax this assumption. So all initial data, which are L2 in the velocity field, must converge to an equilibrium at an exponentially fast rate, and the fluid in particular will go to zero in the topologies of Bessel potential. In particular, will go in W22 in this case. And the proof of this, just 30 seconds, is we were in this scenario, which we had, now the weak solution becomes strong, remains close to the equilibria at all times. So everything boiled down to show that equilibria are either normally stable or normally hyperbolic. And this is what we could not do in the other case that I didn't mention, for lambda 1 equal to lambda 2 equal lambda 3. Okay. And with this, I think I'm done, and thank you very much for the attention.
Giusy for the nice talk. You have